Hello, welcome back to lecture 23. So today we will continue on L-gas HEMTs, high electron mobility transistors or modulation doped FETs. We had introduced a concept in the last two lectures about how modulation doping works and what are the different derivations for the threshold voltage, for instance, or in terms of how the gate controls the 2D EG or 2D electron gas carrier concentration. We took the example of a delta dope channel and we derived the expressions. We talked about the lever rule and how the delta doping layer should come as close as possible to the 2DG interface in order to boost the 2DG concentration. However, if it comes too close, then mobility will start degrading. So we talked about the band diagram and all other things. So today, continuing ahead, we shall discuss a few more things, more practical things, how to make a HEMT more attractive or more useful for a real microwave application. So we will look at both device and process aspects of the same, and we will come to the whiteboard here. Okay, so in the last slide of the last lecture, we talked about the fact that 2D electron gas acts like a parallel plate capacitor with the metal gate on the top, and you can express the capacitance as a just epsilon by d, where d is the thickness of the aluminum gallium arsenide cap layer or the barrier layer plus the 2D electron gas distribution. So if you plot the capacitance versus voltage, gate voltage, I already told you, if your pinch off is say -3 volt, then it will look almost like a rectangle from -3 0 volt. Okay. So this is basically a flat capacitance, it is a parallel plate capacitor and the capacitance does not change with the gate bias, and the area under this CV profile from say pinch off to 0 volt will give you the 2D electron gas concentration under under the gate at 0 volt. Okay. So that is what we discussed, but this is I mean this does not matter whether it is a delta dope layer or it is a uniformly doped L-gas layer. What I mean is that till now we were talking about a delta dope layer where there is a delta doping and there is a 2D electron gas like that. Okay. So this entire layer is L-gas, but there is a sheet of high dope here and you can bring it as close to the 2DG interface as possible to get a very high density of electrons here. However, there is also a uniformly doped concept where essentially if you look at this image or this figure, the entire aluminum gallium arsenide layer is actually doped up till this point. So till this point this is uniformly doped, the entire layer is uniformly doped and this is your spacer, correct, this is your spacer to prevent the mobility scattering, to reduce the scattering. So for uniformly doped layer, if you are doping it uniformly, then the centroid of the doping will be somewhere here. So essentially it is little far away from the 2D electron gas interface. You do not have the flexibility of bringing the centroid of the doping as close as possible, unlike delta doping. So this is not as efficient a doping scheme, a modulation doping scheme as a delta dope layer. In other words, whatever dopant you are getting, the fraction that is being transferred to the 2D electron gas quantum well here would be relatively less than what you would get when you have a delta dope very close to the interface. So what would be the threshold voltage expression for this kind of a device? If you recall, the threshold voltage was derived, this was there is a D here, threshold voltage expression was derived for a delta dope layer. Okay. The threshold voltage for a uniformly doped layer also will look very similar, this term will still be there, this term will have a slight difference, but that is as a home exercise for you. You can derive the expression for a uniformly doped layer also, and it will be very similar to what we had gotten for a delta dope layer. Okay. Now this is about the physics of modulation doping, and you have to understand that this 2DG mobility can be very high, or it is very high if your crystal quality is very good. If you grow aluminum gallium arsenide material at very high quality with MBE or MOCVD, then you are going to get very high mobility, and the reason is, as I told you, the two important scattering here are impurity scattering, which basically is more or less eliminated because the existence of the electron gas is physically away from the dopant layers. So the Nd plus ions actually are physically away, so they do not scatter, the impurity scattering becomes minimal. Okay. So impurity scattering becomes minimal and that can be ignored, and only thing that remains is phonon scattering, which is essentially that the atoms are vibrating in the crystal and they set up a field or a perturbation and that scatters the electron, and we cannot do anything about it. So phonon scattering is the only scattering mechanism that limits the mobility, and you can get really high mobility here. Here we should also keep in mind that the mobility or the phonon scattering would of course depend on the material, and it so happens that if you have indium in a gallium arsenide, it's like an alloy like that, the mobility actually can become better than compared to gallium arsenide. We will come to that when we discuss about pseudomorphic HEMTs, but higher the indium composition, better is the transport property of electron, which means the velocity and the mobility both improve with an increased indium composition. But then the flip side is that it is difficult to grow such high composition of indium content in gas on gas, because you will strain the layer and create dislocations and things like that. So we will come to that in a subsequent lecture, but here we want to talk about more the applied aspect or more the technology oriented aspect of how L-gas HEMTs are useful, and how for microwave application what are the things that we need to take care. So if you recall your MESFET lectures, there is always some kind of a recess, that at least a single recess that we have to do in a gallium arsenide FET, whether it is a MESFET or a HEMT does not matter, because the top layer will always be a highly doped N plus layer, so as to make a good ohmic contact here. It makes a good ohmic contact here. That cap layer has to be etched away for the gate, because the gate cannot sit on the N plus dope cap layer, it will leak. So you have to recess it away and put the gate on the barrier. You see the channel below the barrier, the gate is actually thinner than over here, so that way you have better control on the channel, and that is why you have better GM. And for more aggressive scaling you need that kind of a thinner barrier for better channel control. Okay, you will have a you remember that in MESFET this is the channel, the gate directly sits on the channel, but here this is actually L-gas for instance, and that is why this is your depleted, it is like a dielectric, the channel is here only, it's a channel is only 2D electron gas, so it is very thin, it is probably around 8 nanometer for instance, or maybe 5 to 8 nanometer. Okay, so it is a very thin 2D electron channel, and buffer is gallium arsenide, and then you have a gallium arsenide substrate. Okay, what are the things that you need? You need that the gate leakage Ig should be as low as possible, and for a gate leakage you need a good Schottky contact or a Schottky barrier, and that can be obtained by here, this point the Schottky barrier should be really good. So you can choose there are process steps also in terms of improving the barrier. Also you need a good metal that can actually make a Schottky contact. It so happens that in gallium arsenide people use platinum or gold, and also you use refractory metals if you want to have better gold reliability, better gate reliability. Similarly your barrier should enable a high doping efficiency, which means delta doping for instance is better efficient, it transfers more electrons to the channel. You need a good Schottky barrier, as I told you already. You need a good breakdown voltage, and for breakdown voltage we talked about things like for instance double recess, there is also field plate that we are going to talk about very soon. Okay, field plate is there, and a good Schottky contact of course, so that your gate leakage is minimum. Your good Schottky contact has to be done. The metal work function has to be such that if there is no pinning, by the way, if there is pinning then you cannot do much about it, but you can use a wider bandgap material as a barrier for instance. This cap should be highly doped so that this barrier is not there, and you have a as lowest contact resistance as possible. That helps minimize parasitics. Your excess resistance also should be minimum. That is why a high mobility times 2D electron gas product is always desirable. Your mobility and 2D electron gas both should be as high as possible, so that your excess resistances are minimized. Whenever you turn the channel off, the source and drain will connect through the buffer, so the buffer leakage should be really low. There should be as minimum leakage as possible through buffer, because the moment you turn the channel off, the source and drain will try to communicate through the channel. So your current should be suppressed, or it should be as low as possible. The buffer quality should be really good. The buffer should be as insulating, or I would say semi insulating as possible. Okay, as semi insulating as possible will give you a low buffer leakage current. And of course I told that there has to be high 2D density, there has to be high mobility, this is repeated here twice, and high breakdown voltage. Of course these are the device parameters that you are looking at, so that your overall leakage is low, your transconductance is high, your parasitics are low, and your current drive is better. Okay, all of these conditions may not be simultaneously fulfilled, especially for a basic or a baseline L-gas HEMT. That is why the concept of pseudomorphic metamorphic HEMTs come, which we will discuss in a subsequent lecture. But these are the main targets from a device engineering point of view, that these are things that I want in a device which is going for a microwave application. What kind of application? Of course microwave power and microwave low noise. Typically requirements are more or less similar, except that if you have a low noise application, you emphasize more on the gain, gate length, reduce parasitics, of course. right. You do not talk so much about the power density that you will handle, and of course you need very good gain. If your GM is high, you will have good gain. For good power, you of course need a very large device because you want to carry much higher current, so that you can give, for a given breakdown voltage with very high current, you can get a higher output power current, output power density. You talk about gain, efficiency, and so on. Okay, so there are some slight similarities and slight differences between requirements for power and as well as low noise application. So if I want to summarize what are the things that we want to maximize and minimize in a device, then this table is very, very important, and this holds true for not only LGAS gas HEMTs, but also this holds true for MESFETs. This also holds true for LGAN GaN HEMTs, for instance, especially typically all compound semiconductor FETs that are used for your microwave applications will need this. Okay, this will not hold true for bipolar device or BJT or an HBT even in compound semiconductor, because some of the things will be different there. In a bipolar device, when we will talk, you will see that it is a vertical device, so we do not talk about things like channel resistance in the lateral direction, we talk about in the vertical direction. So there are many things that are different, so we will come to that. So you see ohmic contact resistance RC should be as low as possible, and for that you use the N plus cap layer, as I already discussed. People do alloyed contacts. You have to alloy the ohmic stack, and then it will alloy down and make a good contact. Sometimes people do an implantation of N plus dopants in the layer, so that you can even form a highly doped layer below the ohmic contact. These are all schemes to actually improve the contact resistance. The channel and excess resistance RS RD also has to be minimum to bring down the parasitics. Actually this will constitute a lot of parasitic resistances. You have to minimize that, and for that you need to basically the product of mobility times 2dg density has to be as high as possible. And again your N plus cap layers will help. Choosing materials such as indium gallium arsenide as the channel will also help, that is pseudomorphic HEMT and indium phosphide HEMT that we will talk about. Okay, you want to minimize substrate injection, you do not want any spurious or unwanted electrons or holes being injected by the substrate. So you need to have a quantum well structures. What I mean is that instead of having a 2d electron gas like that, people have 2d electron gas like that, so that the 2d electron gas is confined from both sides, so the substrate injection from back side is also minimized as opposed to here, correct. And also sometimes people use a p-type buffer, a mildly p-type buffer on the back side, so that this barrier is high. You do not have just a one quantum well, you just have a double quantum well, and you have a mildly p-type dope barrier, so that this barrier, the second barrier at the back side, is also large. You are talking about this barrier to the back side, it is also large, and so people use a slight p-type so that the Fermi level can be pushed down, and then you minimize the substrate injection, because substrate injection will lead to early premature breakdown and a poor channel control. Gate leakage I already said has to be minimized. Your LGAS barrier or whatever barrier you use can be higher, so that the band gap can be higher, so that your gate forms a better Schottky contact. People do gate recess, double recess field plates. These are the techniques that people use for improving the breakdown voltage. Of course parasitic capacitances has to come down. You cannot use high K dielectric anywhere, otherwise because of high K epsilon, not epsilon s, this epsilon s is high K, it is high, then your C, because your capacitance goes as epsilon, your capacitances, say the gate drains capacitance, the gate source capacitances, etc., will become significantly higher. It will bring down it will increase your RC delay, and that will also bring down your high frequency performance. That is why we have to use low K dielectrics. We have to use things like air bridge, for instance. I will show you air bridge where you have no dielectric at all, it is just air, because air has the lowest dielectric. Similarly, you have to improve the breakdown voltage, which I already said. People use gate recess, people use field plates, higher band gap materials that are fundamentally higher band gap with a higher critical electric field or breakdown, and finally you need a good control on the threshold voltage. So to have an excellent control on the threshold voltage, because you are going to recess, this here, sometimes people use a layer called an H-top layer, which means it is a different layer that is inserted intentionally, so that when you are doing the channel etching, you are etching something like that, right, sorry, when you are etching something like that, it should stop exactly the place where you want. It should not over etch, it should not under etch. If you want to etch say 15 nanometer, it should etch as close to 15 nanometer, it should not etch say 18 nanometer, it should not etch say 12 nanometer. So that for that control people use a different layer in that here, which is called H-top, which means here, which means whatever gas chemistry you are using finally plasma some chemistry like a fluorine or chlorine chemistry, that chemistry which is the gas chemistry which is etching the L-gas layer will naturally not etch the H-top layer, for maybe a phosphide layer could be there, indium gallium phosphide, that should not affect the band diagram so much. Okay, whatever 2d electron gas density, whatever mobility you get should be more or less the same. However, the etch rate, that will have no etching against the given plasma condition, so that behaves like an H-top layer. And if you have an H-top layer, then you have a precisely etched barrier, you have a precise control on the 2d density, which means you have a precise control on the threshold voltage. So epitaxial layers with very sharp interfaces, an etch top layer for a control and precise gate etch, gate recess etch. All these things help control the threshold voltage to a precise level, and these are very important for microwave performance, microwave device performance. Okay. So, if I talk about ohmic contact, I already said about N plus gallium arsenide contact, but nevertheless if I want to go in a little bit more detail, these images are taken from this book mentioned below here, which I have often quoted here. So, what is happening here is that you have an N plus layer, of course, this N plus gap layer is there, so that you can improve the contact, because it is very highly doped layer, and then there is this L gas barrier, and there is this delta layer, again there is a spacer, and then there is a 2dg here. Okay. So, what are the different resistance? You can consider a distributed network of resistances here, but there is always a resistance of the, maybe I will use the red color here. So, there is always a resistance of the N plus layer that you are using, and that resistance should be as low as possible, which means the N plus layer should be as highly doped as possible. There is this contact resistance as the metal is spiking down. There is of course the channel resistance that comes, the RS, the channel resistance, the source access resistance, and similarly here the drain access resistances will come. So, if I plot across this line, if I plot a band diagram, because I have a highly doped region here, this is your very highly doped N plus gas gallium arsenide, and this is your aluminum gallium arsenide layer, this is your delta dope, this is your 2dg, correct. And you can see that the formation of ohmic contact here, it entails that the electrons from the Fermi level on the metal side will have to go over the barrier, and of course the barrier is reduced, but it cannot tunnel per se as much, and so there is this resistance, the internal resistance that although the metal is alloying and spiking below, there is always this resistance that is provided by the aluminum gallium arsenide layer. So, one of the techniques to actually improve that is that below the N plus gas layer, this is your N plus gas layer, and this is your barrier layer, this is your L gas barrier layer. Between these two layers you have a very thin layer of N plus aluminum gallium arsenide. You are going to use a wide band gap aluminum gallium arsenide, but that is very highly doped N plus, which is just below the N plus gallium arsenide layer. So, what it does is that it does this thing to the band diagram. So, the band diagram looks something like that now, correct, because this part is your N plus L gas, okay, this part is your N plus L gas, and this is your regular L gas. Okay, this is a regular L gas undoped, this is your delta dope layer, this is your spacer, right, and this is a 2dg. So, what is happening here is that because of this triangular nature, it goes something like that, electrons can tunnel here. Okay. So, the electrons can tunnel at this point because it is a thin spike that you are putting in with highly doped L gas layer, and that tunneling will help, then once they go tunnel they will come here. So, essentially your ohmic contact resistance is reduced, or it means it is improved once you put an aluminum gallium arsenide layer which is highly doped just below the gallium arsenide layer. So, this technique is also used for improving the ohmic contact resistance. Okay. Next is a substrate injection. I already said that substrate injection, the buffer leakage should be as low as possible. So, you want that there has to be a double hetero, this is like a double heterostructure, there is a heterostructure here, there is a heterostructure here, because there is a barrier from here and the barrier here, it is better confinement, you get a better carrier confinement, and which means your channel control will be better, and more importantly your substrate injection, your electrons will not be able to spill from source to the drain side through the buffer. If you just have a quantum well something like that, just a quantum well something like that, then electrons here can actually spill over here, correct, but here because of a backside barrier, this is also called back barrier, by the way, this structure is also called back barrier. A back barrier structure will not allow electrons to spill over to the buffer and have a substrate injection. This is especially important for more highly scaled devices like millimeter wave devices as Ka band, Ku band, etc. Okay, and this helps you improve the 3 terminal breakdown. 3 terminal breakdown is measured by basically biasing the gate at a minus voltage, which is more minus 1 volt more negative than the threshold voltage. So, if your threshold voltage is -3, you bias it at something like -4 volt, which means the channel does not exist, and you keep the source grounded of course, and you apply a voltage on the drain, and you keep increasing the drain volt 1, 2, 3, 4 volt, 10, 20 volt, etc. And you will see that eventually, because this channel is blocked, so the electrons will be injected here and they will try to go through the buffer. So, if your buffer is insulating or highly resistive, then your breakdown voltage will be super high, but the breakdown voltage also will depend on this spacing, the spacing between these two essentially. If your spacing comes closer, then your breakdown voltage will also suffer. So, those things also need to be taken care of. Finally, to improve the breakdown voltage, there is this field plate technology. So, if you look carefully from a cross sectional point of view, there is a field plate, this is a metal basically, it is a metal, but it is sitting on top of a dielectric and it is sitting on top of a gate. Actually the gate and the field plate, this structure is called a gate connected field plate, GCFP, gate connected field plate. So, the gate on the side view looks like it is isolated from the metal called field plate, but actually they are shorted. There is a metallic short between the gate and the field plate. Okay. So, you see here in this image, at the end of the device, if this is from the if I say this is from the along the y direction, this is along the sorry, this is along the x axis, this is the along the y axis, this is along the y axis that you are seeing from the side. So, here you are looking from this side, this image you are looking this from this side. Okay. So, you can see that gate is covering up to here, but then there is a dielectric, and then behind the dielectric there is a metallic short that you connect the gate to the field plate. So, the field plate is coming here, but it is actually coming here. Okay. So, essentially you can see this is an extended gate. It is an extended gate that goes beyond the gate drain access region to towards the gate drain access region in a more amount. This is your extension, field plate extension, we call it LFP, how much extension you do. To understand how extension helps, or what kind of dielectric thickness is needed, what kind of metal field plate thickness is needed, width is needed, etc. People do typically simulation, some kind of a TCAT simulation to get an idea, not that it will give you more the best accurate result, but it gives you a trend with increasing field plate length. This is the field plate length, right, this is your field plate length. So, with increasing field plate length, do I get better? What kind of field plate length? Should it be 0.5 micron? Should it be 0.7 micron? Should it be 1 micron? Those kind of idea you will get with a good simulation tool. This structure is, by the way, source connected field plate, SCFP. When you have as source connected field plate, the source is metallically short to the metal here. This metal is not short to the gate now, because otherwise the source and gate will be shorted. So, this field plate metal is isolated from the gate, but it is metallically shorted to the source, and it does not, the wire does not go on top of this like that, but in general you have like dielectric filling up everywhere. Then you open the dielectric, there is a hole, the metal will be exposed in the source, then another metal evaporation will be done, that metal lift off will be done, that metal will come and connect to a field plate here, there will be dielectric of course, and sometimes you can put more than one field plate. Say you can see there is one field plate here, there is another field plate here. If this is a gate connected field plate, then there is a dielectric that will happen here, and then there is another field plate that will come here. So, or this might be say gate connected field plate. Okay. So, source connected field plate, basically you have a source that is grounded, which is metallically short to the field plate, which is extending between the gate and the drain, and in case of gate connected field plate, you just metallically short it to the gate. Both field plates serve the same purpose, which is to improve the breakdown voltage. In many cases people find that source connected field plate helps improve it better than a gate connected field plate, but depends. Okay. It depends on the device technology, the requirements, the application, the process complexities, etc. There are many factors, cannot just put everything under one bucket. You can see this is a scanning electron microscope image of 3 field plates. This is the gate metal, you see this is the gate metal, there is a dielectric, the dark color is dielectric, there is one field plate, there is again dielectric, the second field plate, then again dielectric, then the third field plate. They are all metallically shorted, not here, but at the end of the device there will be metallically, there will be one opening where the gate metal will be metallic short to the field plate 1, to field plate 2, to field plate 3. So, essentially they are the same field plate, but they are extending different ways. You can see this is field plate 1 goes up to here, field plate goes up to here, you are going more towards the gate drain, then again you might have a dielectric, this is the dielectric, okay, which is maybe silicon nitride, then field plate 3 might go up to here, FP3. So, field plate 3 might go here, the field plate 1, field plate 2, field plate 3, and they are progressively thicker away from the channel. Okay, you can see that, right. So, what has field, this metallic short, this metallic short that happens with the gate metal. So, it is like an extended drain, extended gate in this case, this is like an extended source in this case. Okay. So, these field plates do one thing, they tailor or they engineer the electric field profile, in the gate drain region. Remember, the gate drain region is where the avalanche initiation will take place, because the edge of the gate is where the field is high, F max. The highest electric field always happens near the gate edge of this edge towards the drain. So, if you plot the electric field, okay, along, this is the gate edge. So, this is the gate and this is the drain, for instance, the electric field will always peak like that. Okay, the peak electric field will be something like that, and then it will drop. So, this is the critical point, because the electric field is the highest here, F max is the highest here, and this point will reach the critical electric field F max critical, in the critical electric field of breakdown the first, and once that reaches, then the device breaks down, and the area under this gives you the breakdown voltage. This is the spacing x along the gate drain direction. So, what field plates do is that they tailor or they smoothen out this electric field profile. How that what happens is that if you have a, suppose a gate, and then there is a dielectric, and you metallically short another metal which is coming here like a field plate field plate 1, and just you have one field plate, okay, but the field plate will be on top of the dielectric. So actually this is not a very correct figure. So you have gate, okay, and then what I will do is that I will use the blue color, so that your dielectric is this is your dielectric, like silicon nitride for instance, and then the field plate metal will come out, which is this is the field plate metal, okay, and you can see that the field plate metal is away, physically away from the surface, L gas surface compared to the gas, okay. So what is happening is that at this edge the electric field profile is reduced and electric field profile is introduced at this edge also. So what happens is that initially the field profile looked like something like that, but after putting the field plate the electric field profile would look something like that. So you have a peak here and you have a peak here, but it is smoothened out, or it is not completely smoothened out, but it's you distribute the electric field at 2 points. So the peak field comes here and it there is a peak here, there is a peak here, but the area under this can now be more, because now you can go to higher voltages. When it reaches this point it will have something like that. So the area under that curve is actually much more than the area under the red curve here, okay. So your overall breakdown voltage, which is the area under the curve, increases, okay. This is the funda behind field plate. In a more qualitative aspect you can say that there is a gate here, okay, there is a dielectric here, there is another gate here for a gate connected field plate, okay. You can say there is another gate, it is metallic shorted only. So what happens is that, and this is your 2dg, okay. So suppose this is some thickness d, okay, and the silicon nitride here could be 100 nanometer, or depends, that silicon nitride. So this is d. So for this the 2dg density, the 2dg location to the gate metal location is d, but for this gate the distance from the minimum distance from the 2dg density, 2dg gas to the metal is actually d plus the silicon nitride thickness, t silicon nitride, which could be 100 nanometer. So for this gate the pinch off, because it is very high thickness, so your capacitance below this gate is actually epsilon naught epsilon s by d plus t sin x, silicon nitride. So this is a large number, d could be say 10-20 nanometer, but silicon nitride could be 100 nanometer. So in that case this capacitance is very low, the capacitance for this secondary gate, I am calling it a secondary gate instead of a field plate. The capacitance is very low, which means your threshold voltage has to be really very high in terms of negative voltage, because if I say that the area under the CV is constant, which means the 2d electron gas density is more or less constant. So 2d electron gas density is suppose 10 to the power 12 here, 2 into 10 to the power 12, it should be also 2 into 10 to the power 12 there, okay. So if I look at the CV curve, this is suppose minus 3 volt for the main gate. So main gate, it goes like that and like that. The area under that gives you the 2d electron gas density, which is 2e12. Now the capacitance for the corresponding gate, extended gate, as I told you, this capacitance is very low, this capacitance could be here. So if the capacitance is very low but the area has to remain constant, which means the threshold voltage will be much lower, this is not up to scale, this could be say minus 10 volt, okay, but so that the area is constant. So what happens is that, maybe I will keep this again here, okay, what is happening is okay. So what is happening is that you have a gate here, then you have a dielectric and a secondary gate. So below the primary gate your threshold voltage is suppose minus 3 volt, below the secondary gate the threshold voltage is suppose minus 10 volt. Suppose what it means is that, but both of the gate are metallically short. So whatever voltage I apply, suppose I apply a voltage of minus 3 volt. So what happens is that, if I use a blue color here, what happens is that your 2d electron gas is something like that. No, if you apply a gate voltage of minus 3 volt, then this part is depleted completely depleted. However, this part is not completely depleted, it needs minus 10 volt to deplete, which means at minus 3 volt it is only partially depleted. So maybe instead of everywhere is 2 into 10 to the power 12, below the gate has become 0 now, because I apply minus 3 volt and pinch it off. Maybe in this region it could be say 0.8 or 0.9 into 10 to the power 12, you see. So essentially you have no 2dEg in the normal case, you have no 2dEg below the gate, and below and just outside the gate you have 2 into 10 to the power 12. But in case of a field plated HEMT where you have an extended gate, you have no 2 dg below the 2 dg is not there for below the gate, but here you have say 0.8 into 10 to the power 12 and below beyond the field plate you have 2 into 10 to the power 12. So, what you see what is happening is that your 2 dg concentration is not there, then it is slightly there, then is more there. So, you are gradually changing the 2 dg concentration. This helps improve the field profile and improve the breakdown voltage, because remember higher the carrier density, lower is the breakdown voltage in general qualitatively. It is more difficult to deplete a highly conducting layer, it is relatively much easier to deplete a lower dope layer. So, this part is like a lower dope you can say, okay, and so you can deplete that more easily without going to breakdown. This part is more difficult, of course, that is why if you have multiple field plates, field plate 1, field plate 2, field plate 3, then you have more freedom, like this could be 0.6 into 10 to the power 12, this could be 0.9 into 10 to the power 12, then beyond that could be 1 into 10 to the power 12, then 2 into 10 to the power 12. So, you have a 2d electron gas density which is gradually increasing. Okay. So, you are able to gradually push the breakdown voltage more and more, instead of suddenly depleting 2 into 10 to the power 12, you are gradually increasing the doping. So, breakdown improves. Okay. So, this is the qualitative picture of the field plate helping the breakdown voltage improve. So, field plate is a very common technology in not only gallium arsenide HEMTs, but also in gallium nitride HEMTs that we will talk about in subsequent week. Okay. So, with that we will come to a conclusion of this lecture 23 about HEMTs, where we talked about different technology aspects in terms of breakdown voltage, gate leakage, substrate injection, double quantum well, and ohmic contact resistance and so on. So, we have one more lecture 24 remaining for L gas HEMTs, which we will do in the next class. Okay. So, thank you for your time and I will see you in the next class.